Welcome to Modeling Mastery, the podcast where we explore the art and science of software design. I'm Hex.
And I'm Byte.
We've now covered the three core types of objects in tactical design: entities, value objects, and domain services. These give us the tools to model the things and the stateless actions within our domain.
Now, in Chapter 8, we're going to explore one of the most powerful and transformative patterns in modern DDD, domain events. This pattern was not formally part of the original Blue Book, but has since become an essential tool for building decoupled, scalable, and resilient systems.
It's a fundamental shift in thinking. A domain event is an object that represents something significant that happened in the past. Instead of just modeling the current state of our system, we start to explicitly model the state changes themselves as first-class citizens of our domain.
This chapter will show us how to discover, model, and publish these events. We'll see how they enable loose coupling, facilitate eventual consistency between different parts of a system, and provide a rich history of everything that has occurred in the domain.
It's a pattern that unlocks many of the advanced architectures we discussed earlier. Let's get started.
So far in our journey through tactical design, our patterns have focused on modeling the state and behavior of our domain objects. But there's another critical aspect of the domain that we must model: the significant occurrences and happenings within the business. This is the purpose of the domain event pattern.
The book's definition is both simple and profound. A domain event represents something that happened that domain experts care about. It's not a command telling the system what to do in the future. It's an immutable, unchangeable record of a fact, something that has already occurred. This distinction between a command and an event is absolutely fundamental to understanding this pattern.
And that distinction is captured directly in the ubiquitous language, specifically in the naming convention. A command method on an aggregate might be named commit backlog item, which is an instruction. But the event that results from that action is named in the past tense, backlog item committed. The name itself declares it as a historical fact. You can reject a command, but you cannot change a fact that has already happened. This is why events, once created, must be immutable.
The real power of domain events becomes obvious when you consider how systems traditionally communicate and the problems that arise from it. Without events, if one part of a system needs to trigger a reaction in another, the first component must have direct knowledge of and call the second component. For example, when an order is confirmed, the order service would have to know about the shipping service and the notification service and call them directly.
That creates a web of tight, brittle coupling. The order service becomes a central point of control, and its responsibilities grow over time. Every time a new system needs to know about a confirmed order, you have to go back and modify the order service code. It violates the single responsibility principle and makes the system hard to change.
Domain events completely sever that tight coupling. With an event-driven approach, the order aggregate's responsibility ends when it successfully confirms the order. Its final action is to simply publish an order-confirmed event into the void. It has no knowledge of who, if anyone, is listening. This creates both loose coupling and what we call temporal decoupling. The order process can complete without waiting for shipping or notifications to finish.
This makes the entire system incredibly modular and extensible. A year from now, if the business decides the data warehouse also needs to know about confirmed orders, you don't touch the existing ordering code. You simply create a new independent subscriber that listens for the order confirmed event and pipes the data to the warehouse. The original component remains unchanged.
So where do we find these events during our modeling sessions? We listen carefully to the domain experts. The book suggests paying attention to specific phrases they use. When an expert says, "When a backlog item is committed, we then need to update the sprint's burn-down chart." Or, "If a customer's payment fails, we have to notify them immediately." Those are bright flashing signals. Those when and if statements describe the business processes and reactions that are perfect candidates to be modeled as domain events.
It becomes clear then that a domain event is not just a technical pattern for sending messages. It is a full-fledged first-class citizen of the domain model. It represents a meaningful business occurrence captured in the ubiquitous language. It is the primary mechanism we use to model the dynamics and processes of the business, enabling us to build systems that are not just a collection of static objects, but are reactive, resilient, and true to the domain they serve.
We've established why we use domain events for achieving loose coupling. Now let's transition to the practical details of how we model and publish them. When we create an event object, what should it contain?
That's a critical design question. An event is essentially a message, and that message must be self-contained and meaningful to its consumers. A subscriber shouldn't have to make a separate call back to the source system just to get the information it needs to react. The book shows that a well-designed event object, such as the backlog item committed example, carries a few essential pieces of data to provide this context.
The first and most fundamental property is a timestamp, an occurred on date, to record precisely when the event happened in the domain. This is the very definition of a historical fact. Second, and just as important, the event must contain the unique identities of all the relevant aggregates that were involved in the occurrence.
Exactly. For the backlog item committed event, this means it must hold the tenant ID, the backlog ID of the item that was committed, and the sprint ID of the sprint it was committed to. This gives any subscriber the complete context of what happened and to which specific objects. The event might also carry other useful data from the transaction, a practice sometimes called event enrichment, which further reduces the need for subscribers to make extra queries.
And because an event represents the past, which cannot be changed, the event object itself must be immutable. This means all of its properties are set once in the constructor, and the class only exposes getters. It is, for all intents and purposes, a value object that describes a moment in time.
So we have this rich, immutable event object. The next logical question is, where does it come from? Who in the model is responsible for creating and publishing it?
The book is very clear on this point. The most appropriate source for a domain event is the aggregate itself. An aggregate is the consistency boundary and the source of truth for its own state. Therefore, it is the one that should announce its own state changes. Publishing an event is the final action of a successful command method.
Let's walk through that. A client calls the commit to sprint method on a backlog item aggregate. Inside that method, the aggregate first enforces all its business rules and invariants. If they all pass, it updates its internal state, for example, by setting its sprint ID. Then, as its very last step, it announces this fact to the world by creating and publishing a new backlog item committed event.
And for the publishing mechanism itself, this is another critical design point. We must keep our pure domain model completely decoupled from any specific infrastructure, such as a message queue or an email client. To achieve this, the book presents a simple and elegant in-process solution, a lightweight static domain publisher that implements the classic publish-subscribe pattern.
It's a clever design that uses a thread local variable to manage its list of subscribers. This means subscriptions are scoped only to the current requester thread. The application service, before it calls the aggregates command method, first registers any interested subscribers with the publisher. Then, when the aggregate eventually calls publish, the publisher simply iterates through the list of subscribers registered for that specific thread and notifies them.
It's important to stress that this is a synchronous in-process notification system. The subscribers are called immediately as part of the same transaction. This is an incredibly powerful technique for decoupling different components within the same bounded context. Spreading the news to remote systems is a separate, more complex challenge that builds directly on this foundation. The lightweight domain event publisher we discussed is excellent for decoupling components that operate within a single transaction. But the true transformative power of domain events is realized when we use them to communicate between different bounded contexts. This is how we build truly autonomous, loosely coupled systems.
Right, and to do that, we need to get the events from our model out into the wider world, typically by using an external messaging infrastructure like RabbitMQ, Kafka, or a cloud-based service. But this introduces a significant technical challenge that every developer working with distributed systems must face: the problem of dual writes.
Can you break that down for us?
The dual write problem is this. How do you guarantee that a change to your aggregate's state is successfully committed to your database and, in a separate action, the corresponding domain event is successfully published to the message queue? You can't wrap a database commit and a network call to a message broker in a single, simple transaction. If the database commit succeeds but the message publish fails, your systems will become inconsistent.
This is a classic distributed systems problem. The traditional and often problematic solution is to use a distributed transaction, also known as a two-phase commit or an XA transaction. However, these are notoriously complex to manage, can have a significant performance impact, and are not universally supported across all technologies. They are often a last resort.
Exactly. This is why the book advocates for a much more robust and elegant pattern to solve this problem: the event store. The core idea is to create a dedicated storage mechanism, often just a single database table, within our own bounded context database. The sole purpose of this table is to store a serialized record of every single domain event that our model publishes.
And the implementation is quite clever. A generic in-process subscriber listens to our domain event publisher. When an aggregate publishes an event like backlog item committed, this subscriber immediately catches it, serializes it, perhaps to JSON, and appends it to this TBL stored event table. Because this subscriber is running in the same thread, this append operation happens as part of the same local database transaction as the original aggregate's state change.
And that's the magic right there. The state change to the backlog item and the recording of the backlog item committed event are now guaranteed to be atomic. They either both succeed or they both fail together. We've solved the consistency problem without needing a complex distributed transaction. Then, a completely separate out-of-band process, like a background timer, can periodically read unpublished events from this local event store and safely forward them to the external message queue.
This pattern has other profound benefits beyond just ensuring reliable delivery. This event store becomes a perfect, durable, and unchangeable historical archive of every significant business occurrence in the domain. It's an invaluable audit log that can be used for debugging, for business analytics, and, as we'll see later, it's the foundation for the event sourcing pattern.
So the event store acts as a transactional outbox for our domain. It elegantly decouples the act of an aggregate publishing an event from the technical details of delivering that event to the outside world, making our system far more resilient and providing a rich historical record as a powerful side effect.
We've established the event store as a reliable transactional outbox for our domain events. Now we need to tackle the final step. How do we get those stored events out to the remote bounded contexts that need to consume them? The book outlines two primary architectural styles for this.
The first approach is to publish the events as a RESTful notification feed, which works very much like an RSS or Atom feed that you might subscribe to for a blog. This is a pull model. The bounded context that owns the events exposes a series of paged read-only resources, and it becomes the responsibility of the remote clients, the subscribers, to periodically pull these resources to check for new events.
Let's walk through how that works. A client starts by making an HTTP GET request to a well-known URI to fetch the current log of events. This log is a page containing the most recent events. Crucially, as the book explains, this resource representation includes hypermedia links, specifically a link to the previous log. This allows a client to traverse backward through the entire history of events, page by page.
This is a key part of the design. Each client is responsible for tracking the unique ID of the last event it successfully processed. When it pulls the feed, it navigates backward through the logs until it finds that last processed event. Then it can walk forward again, processing all the newer events in the correct chronological order until it reaches the end. It's a simple but very robust way for many different clients to consume the same event stream at their own pace.
This REST-based pull model is excellent for fan-out scenarios, where you have many different subscribers interested in the same data. It also leverages standard web infrastructure like HTTP caching to reduce the load on the publishing server. The main trade-off, of course, is the latency that comes with any polling-based approach.
For lower latency, we can turn to the second architectural style, a push model using dedicated messaging middleware like RabbitMQ or Kafka. In this pattern, a background process in our publishing system constantly reads new events from our local event store and immediately pushes them as messages to an exchange or topic on a message broker.
Remote systems then become subscribers directly to that message broker. As soon as an event is forwarded, the broker pushes it to all interested subscribers. This is much closer to real-time and is a more natural fit for use cases that require immediate reaction. It's also better suited for distributing a workload across a pool of competing consumers like a queue.
However, this push model introduces a critical responsibility for the subscriber that the book highlights: message deduplication. Most enterprise messaging systems provide an at least once delivery guarantee. This means under certain failure conditions, like a subscriber crashing before it can acknowledge a message, the broker will deliver the same message again.
This means subscribers must be designed to be idempotent. An idempotent operation is one that can be performed multiple times with the same result as if it were performed only once. In practice, this usually means the subscriber needs to keep a record of the unique IDs of the events it's already processed. If a message arrives with an ID that it's already seen, it simply acknowledges the message to remove it from the queue, but ignores it, preventing a duplicate business action.
It's an essential part of building a resilient, event-driven system. So whether we choose a pull model with REST or a push model with messaging, the event store provides that reliable, consistent foundation. It empowers us to share the important happenings of our domain, which is the key to creating truly decoupled and autonomous systems.